Okay, well, maybe get going. Any questions from last time? We didn't record last time. Forgot to record. I know you'll be devastated. You won't be able to go back and look at those videos, at least for this year. Anyway, we're online now. Anything we need to take care of before we get rolling? No? Career fair still? Stuff going on? Kind of light today. So, so far we've talked about multiphase transport. So the physical motion of two fluids, sometimes both traveling at the same time, liquid and DNAPL, or liquid, water, and air. Sometimes only one phase traveling and the other locked in place. That would be the case in these figures on the upper portion here, where you have below the water table groundwater transport, dissolving components, and then carrying it dissolved as a plume. So far, I guess if we take stock when we're dealing with what we've dealt with so far, we know that if we, revisiting Darcy's law again, just to see where we are. Edward Derivin. Work in terms of pressures. If we have single phase flow or double phase flow, it doesn't particularly matter. Q1, Q2, we've called it. And so we can write Darcy's law as Qi equals a relative permeability, an actual permeability, a viscosity of that fluid. If it's water, then I would be the behavior of water, a pressure gradient, and a length. If we wanted to get an advective velocity, we can take, this is the Darcy velocity as well, we've called it. If we want to get an advective velocity, we can get it from the Darcy velocity divided by porosity. And that's useful to us because you've used it already, because you know that velocity is equal to length over time. And so therefore, length traveled is equal to velocity times time, supposedly, right? It's okay. And if we want to multiply this by area to get a volumetric flux of water, which is, so these can be for multiple fluids, we know that. Sometimes one fluid is immobile, such as NAPL caught by meniscus forces when it's in low saturations. If they're both in roughly equal saturations, we know that both can flow. But now, I guess what we're talking about for contaminant transport is having water as the transiting fluid, NAPL being present in saturation in this chimney at relatively low saturations, having lots of contact area with the water that's flowing past it, and therefore being able to pick up dissolved components. The water is a solvent for it, and it's carried downstream as a plume. And so now we're perhaps interested in water transiting. And so the volumetric flow rate would be equal to area times Qi, which would be water, which is the same as area times the Darcy velocity. And so if we can get this, so we can get from Darcy's law, we can get a flux. If we know things like how the water table is sloped and what the permeability is and what the fluid that's flowing is. If we can get the Darcy velocity, we can get the advective velocity. If we have the advective velocity, we can make a picture that we've had before for length traveled in a given time. And if we have the volumetric flow rate, we can have the mass transported, which is equal to the volumetric flow rate times the solubility, let's not use that, concentration. So milligrams per liter of whatever TCE is in the system. So, for instance, as units. So volumetric flow rate is, if it's in SI, it would be, or so if we have this in grams per meter cubed, and then we have this in volume per unit time, then that gives us a mass. So this would give us probably not kilograms, but kilograms per second as the mass flow rate. The mass flow rate of the dissolved components. This is the volumetric flow rate of water. This is the loading of whatever concentration is dissolved in water and travels downstream, and therefore this is the mass arriving at a compliance point. And so this concentration, the maximum would be what we'll refer to as the solubility. So you put some of it in water, the maximum amount that will dissolve in, so long as the surplus of that component in free phase will dissolve. So that is kind of a preamble, I guess, for us to be able to now look at this behavior. And I'm going to draw it the other way around. Not a very good circle. Even worse circle, that's better. So this is this. So you've surmised already, and I guess these are the questions we're going to ask ourselves, is if you have at this upstream boundary a certain concentration. So a couple of figures. Imagine this is time, and this is concentration. So imagine that you put into here, where there's water flowing at some flow rate, Darcy flow rate, and which is equivalent to an advective velocity as well. We can calculate all these. These two are the same as each other. And VA is equal to Darcy velocity over porosity. So you can imagine putting something in here at time 0, which is this pulse. And so this is concentration relative to some initial concentration, which we can call 1. This is time t0, if you like, when it starts. And you've already done this. You've calculated the magnitudes of this as it goes down gradient. And you did this for Yucca Mountain, or what was Yucca Mountain. And merely from this, that the length traveled is equal to advective velocity times time. And at this downstream location, so this is again time, not distance. So this is C over C0. And you've ended up with And so I guess if this is the total x total, then you can also rewrite this as t arrival is equal to length traveled, which is x total, divided by velocity advective in the x direction. You've used all these relationships. And so now, I guess, what we're going to ask, these are simple ways of looking at it. I guess we're going to ask, are these true? They certainly make sense. And if not, then why not? So there are a couple of things that we have here. We have one. The shape of the plume. Is it really this step function, or is it got something in it that would be along the core? Whoops. So obviously this is the input function. So there's nothing sitting upstream until you dump something in the ground. All of a sudden, concentration goes up to some magnitude. If it's relative to the maximum concentration the water can take, we call that 1, relative concentration of 1 versus 0. Once it's turned on at time t0, it's free to go downstream. At time, a small time, it would look like this. A larger time, it would look like this. Interesting. I'm not going to, so this would be T1, T2, T0, I don't know, T actual, I don't know. And so that's what it would look like in the core. So I guess if you looked at the core, it looks like it's going in, bending around a corner. So I guess within the core, at some stage, this would all be covered in whatever. This would be C over C0 equals 1, C over C0 equals 0. Hasn't arrived here yet. Pristine water. So that was what this would look like. And here, you're still waiting for it to arrive, still waiting, still waiting, still waiting. When it gets down to the end, all of a sudden, if it comes down different tubes, you end up with a stair-step view of this, as you've already seen. But so what are the ordinates of this? Is this always a nice sharp front like this? The answer is no, not always. When will it not be that case? And can we put some limits on that? And the second point is the arrival time. Also one sharp like this. And is it also T arrival equals total length divided by advective velocity? So does it look like this? Or should it look something like this? And whoops. And this. And it will look like the green line. But then the question, and it will also look like the blue line. But the question then, what are the limiting conditions that cause it to look like that? And so that's what we'll talk about today. So we'll talk about the mechanisms, more complex mechanisms by which we can understand this behavior. Say definitively when it looks like the blue curve in terms of arrival at a compliance point, and when it actually looks like the green curve because of processes that are acting. So that's where we're going today on our new journey. So if I go back here, so I guess that was both a recap and a kind of a look forward. So we're going to look at transport. So it's important to make the mental change that now we're not looking at two fluids traveling at the same time. We're probably looking really only at water traveling in the saturated groundwater zone and carrying dissolved in with it something that really doesn't affect its motion. It's not heavy enough to stop it. It doesn't affect the permeability behavior very much. And so we can work with that. So we'll look at what the transport mechanisms are for advective flow and diffusive flow. So we'll look at each of these transport mechanisms in turn. We'll look at what the physical processes that affect these two behaviors. And we'll find out that this dispersion is related to mechanical effects and also to mixtures of diffusion and dispersion included together. So we'll try and explain exactly why those curves might look like the way they are. This is what we're looking at. We've got some free phase material in the base that can dissolve. It'll be carried by the motion of the groundwater, which is traveling at the advective velocity in some direction. And this is what is moving it from its located site. It's dissolved in the water in relatively low concentrations. And we can look at these two main mechanisms. The first you've already dealt with, right? We've put down these equations. The velocity is length traveled divided by the time taken to do it. And so it'll travel a distance given by the product of those two, perhaps, to first order anyway. But operating on top of this, we've got these other effects of both diffusion and mechanical dispersion. And so I think the best way to explain this is diffusion is if you take this Gaussian distribution on its side and you drop a drop of ink in a beaker. And so if you drop that ink in the beaker and draw across it, then the concentration versus radius across that drop would look like this delta. Basically a delta function. 100% concentration in the drop. Of course, ink's just pigment and water itself, I guess. And 0% concentration out there. This is at time t0. And as you wait for something to happen, it goes to this, and then it goes to this. And of course, you know that what's driving this is Fick's law. Concentration with space, dr, I guess, but let's call it dx. And you know that Fick's law is given by a diffusion coefficient times a concentration gradient with a minus sign in front of it. D is diffusion coefficient. Meters squared per second, I think, are the units, but let's not worry about that for now. But most importantly, this would be the ink drop, and it would slowly spread. Ultimately, at time infinity, I guess, it would look like this, dead flat, across the whole beaker, and the beaker would be very milky blue if it was a blue ink that was in it, and different from the initial starting point. This has zero gradient, so nothing is being physically transported in space. It's steady state, it's reached its completion. And so that's one way to think of diffusion. If you want to think of what advection is, then advection is taking that container that has the drop of ink in it and me walking across to the other side of the classroom, physically moving it with the water from one location to another. So the difference between those is that this is by a concentration gradient that carries it. This is being carried by the bulk velocity of the water, physically taking the beaker to the other side of the room. And so those two processes are separate. If I was carrying the beaker, I guess it would be diffusing at the same time I was traveling with it. And so by the time I got to the other side of the room, it would look like one of these bell curves, these Gaussian distributions. And so the other thing that operates in these systems is called mechanical dispersion. And mechanical dispersion is the idea that if you flow fluid through a porous medium and you put a drop of fluid in a dye in there, then what it will do is two molecules of dye adjacent to each other, one will go off in one direction, one will go off in the other direction somehow. And so if you draw a section across this and plot the concentrations, it's going to look like this. And so the idea that for mechanical dispersion, you start upstream and you take a slice across this, it will look exactly like this. You go downstream, take a slice across this, it'll be like this. And so if you transfer that to this idea, then mechanical dispersion is a diffusion-like process. And if it's a diffusion-like process, perhaps we can represent it as a diffusive process just by using a different coefficient to represent these behaviors. That's really what we're doing. So advection carries it. It would carry it just as a bead. Nothing would happen to it. I guess with the progress of time, it would spread out in the beaker. But if we think about that as being a piece of dye traveling in a porous media, this is the mechanism by which we get spreading, mechanical dispersion. And so you can think about this going from upstream to downstream over some length. It takes a certain amount of time to get from upstream to downstream if it's being carried at some advective velocity. And if you sampled it downstream after seeing it upstream, you wouldn't be able to tell whether it had been mechanically mixed or whether it was just diffusion. I guess that's the kind of take-home message. So the bottom line is we can deal with diffusion first to understand how that behaves. By adding a different coefficient to allow for this dispersion, we can incorporate that process as well. And then we can talk about how we represent advection to put it all together in a single expression that defines this behavior. Okay. So this is it. Diffusion, we already said this. Nature abhors gradients and wants to get rid of them. Likes to reduce the concentration gradient by flattening it out, by transporting it. High concentration drives a large mass flux. The mass flux is the dissolved pigment in the ink that you put in, and it conforms to Fick's law in that this is the mass flux, this is the diffusion coefficient, length squared over time, meters squared a second, and the gradient in mass per unit volume, typically, and a length over which it travels. So this is mass per unit volume, milligrams per liter, or kilograms per cubic meter, whatever it is, and x is in length. And so typically the magnitudes of diffusion coefficient are around 10 to the 9 meters squared a second. And that is for liquids, open liquids. So putting a drop of ink in a swimming pool, this would be the rate at which it would spread out to get rid of the concentration gradient. So just like in any good prospect, we can write that we did it for Darcy's law. I hate to bore you with 303 again, but you remember that in Darcy's law, we took Darcy's law, we took this, and we merely dumped this in here. This was the term that became the accumulation. So that's exactly what we do here. Instead, we take Fick's law. I'm not going to use these equations. In terms of a mass flux, this is a fluid flux, which is equal to, I guess we need the minus sign in here, minus diffusion coefficient, concentration gradient. And we put it into the same relationship. Seems strange. For Darcy's law, fluid flow. We conserve fluid mass. Contaminant flow. We conserve dissolved mass. So that's why we can use kind of the same conservation equation. This, as you remember, says mass rate of liquid in versus out equals accumulation of mass of liquid. For Fick's law, we can use the same conservation equation, but it represents mass of dissolved mass into the system versus dissolved mass rate out has to equal the accumulation of that dissolved mass in the control volume. That's all it is. So control volumes are kind of important to us. That's why we talked to them about them early in your career. So if you substitute this into here, you get a relationship that says, instead of being defined in terms of, this would be dP, this ends up being dP d2p dx squared equals, it's not specific storage, it's equal to some compressibility dP dt. Right? This is an equivalent groundwater hydrology equation written in terms of pressures. Instead of having an equation for pressure diffusion written in terms of pressures, we have an equation written in terms of chemical diffusion in terms of concentrations. So you can see that this originally looks a bit like this. Don't need to know anything more than this. So we end up with what's referred to as a diffusion equation, which is exactly what we said before, I think. And we'll never solve these or worry too much about them, but just need to know what they are, which says that once we've substituted Fick's law into this conservation equation, this says that dissolved mass rate in minus dissolved mass rate out equals rate of accumulation of the dissolved mass. And we can solve that for some boundary conditions, which we'll find useful to do. So that's a useful observation. The other thing is that if we write Fick's law and we use a value of diffusion just for pure water, that would be, if I had a drop of ink here and this room was filled with water, it would be the rate at which that would diffuse to you in a swimming pool. But when we're talking about the subsurface, the swimming pool is kind of filled with grains of sand. And so rather than using the free phase, if you like, or free fluid diffusion coefficient, which you can get from a textbook, we have to modify for the fact that the diffusion is only occurring within the liquid, which is only present as it winds between the pore throats between the grains. And so the effective diffusion coefficient that we might think we would use, you'd kind of think it would be less. One, because there's less cross-sectional area for it to go across. It's not being carried by the velocity of the water faster because it's squeezing across that. And secondly, in going from A to B, it has to go this tortuous path. It can't just go on the motorway, but it has to go on the side roads to get there, around the grains. So this tortuosity makes its direct path longer. It's not as the crow flies. And so you can imagine that if you take this term out of your reference book in the library for whatever stuff is diffusing in water or whatever other solvent it is, you have to modify it in some way. And you can modify it by multiplying it by a coefficient that relates to tortuosity. And you'd expect that this tortuosity would somehow be proportional to the length traveled versus the actual as the crow flies length. And so this is the length actually traveled. This is the length between 2 points, kind of a fractal idea that as you go from one place to another on the coastline, if you go up all the inlets, the surface has some kind of dimension. And this is a different idea. And so take it on trust that this multiplier that you might want to use to go from the term that you get out of a reference text to one that you might use in the subsurface might be a factor of 100th or a half. This is half to a 100th. So you can just modify this by some term. And let's leave it at that this moment. It's important to understand why we might use it. And the reason is because the length traveled is actually longer than the as the crow flies distance. If we do have a number that we can use for a porous medium, then if we use one that's representative of the porous medium, it should represent the rates at which that diffusion would occur between me and you if the room was filled with sand grains and water. And so we can solve this equation with the effective diffusion coefficient, and we can solve it for a geometry where we take, the geometry would be the one we've drawn before. The geometry would be this. This would be relative concentration, C over C0. This would be 1. This would be at time 0. This would be radius. And this would be the boundary conditions, or as we choose them. And then over time, what we'd expect would be that solving this differential equation for initially a concentration that's 0 at r equals 0 and at time t, and then all of a sudden making it 1 at this thing. In other words, this skyscraper. I guess I could have drawn it in blue. So T0, it doesn't exist. T greater than or equal to 0 as it comes up. So this is the same as the step input we had before. Yeah, if I jump back to this, I'll come back. This idea here, right? Initially, there's no concentration here. In time, all of a sudden, it's turned on and kept on for all time. So that's what we're doing. And not worrying about the equations, the results for that is this bell curve. The same curve that grades get distributed on, the normal probability distribution. It turns out that that is the solution for this second order PDE for radial diffusion. So this is x squared, but also sometimes we're interested in it going outwards in all directions. It turns to be much the same. This is the equation that represents that. This is the, so if you go out from here, this is the concentration in time. This is, I guess, it comes from this. So for a step input like this, the bell curve, as it evolves, I want it to peak right at the peak. That's good enough. So this is the cumulative probability distribution. So this, if you take this point and go here, some distance, then the area under this curve is this height here. If you go to the mean, the area, I'm going to do it in green. If you go all the way to this point here, then this represents this. This is a cumulative distribution function. So 50% concentration versus this. And if you go all the way, if I go red, so if you go all the way here to here, then this would be 100%. So this is a PDF, probability density function. This is the cumulative probability function, density function. And it gives you a concentration which is equal to this. So this is the case where you hold this constant at 1, and you want to know at any particular distance x what the concentration is. Not that we'll use this for now. And so if you want to know what this is, that is this concentration, it's a function of the location, which is here, and it's a function of how long it is since you introduced it, and it's a function of the physical characteristics of the system, which is this diffusion coefficient. If it's a big number, then it goes from being an ink spot to being flat in no time at all. If it's a small number, it takes forever to diffuse. So those are the constraints on it. And so we'll perhaps think about this, keep in mind the fact that this diffusion behavior is exactly as such. If we look at advection, advection is the simple one that we've dealt with in terms of this behavior here. We're not quite sure whether it matters, it works all the time, because we've questioned whether this distribution of a front really looks like a distribution of a front like this, if this is x concentration, or whether it might look like this. Don't know. So we need to do something more sophisticated rather than just use this velocity being length over time and length being equal to velocity times time. So we can also write a conservation equation for this. If we want to get the advective velocity, we can from coefficient of permeability. This is hydraulic conductivity, which you know. Meters per second, porosity. So this is just equal to Darcy velocity divided by porosity, right? This term here, negative sign. And so we can always get the advective velocity for a system. You can always get that. We also know that the flux carried by advection is going to be, you've probably used to seeing it as the Darcy velocity times the concentration. And we know that the mass flux is equal to the flux per unit area equals area times VD times concentration. You already used this. So this is the mass flux in the x direction. It's written here because we're using the advective flux and porosity, but this is also just the Darcy velocity, right? So perhaps I'm making more. So the flux per unit area of solute is equal to the Darcy velocity multiplied by its concentration. If you multiply by area on both sides, then these two terms become volumetric flow, and this becomes volumetric flow, volume per unit time, mass per unit volume. So it becomes mass per unit time. Again, doesn't matter too much. If we take this and throw it back into our conservation equation, remember we said that conservation equation for flow we could write in terms of mass flow rates of liquid or mass dissolved solute. We chose to do the latter and did this substitution. So we'll do exactly the same here. Throw it in, move it around, and we get a new term. All that matters is this final term at the bottom. This says that dissolved mass rate in minus dissolved mass rate out equals dissolved mass accumulation. Accumulation rate, I guess. So conservation equations are kind of important. So I don't think I don't care so much about this. So we have a couple of partial differential equations. We can combine them. And we will typically write this expression as I'm going to write here. I think I've got enough space to do it. And that is the accumulation of dissolved mass is equal to so this equation is a first order partial differential equation. It represents moving it along with the velocity of the water. This is the advective velocity. And so if I look at, say, a coordinate system in plan view, so imagine we're looking at a plume that starts off here. You can imagine that the plume, as time progresses, would develop like this, that this might be an x direction and this might be a y direction in plan view, looking down on it. But we could also call this longitudinal, and we could also call this transverse, L and T. And that's useful because this plume has some kind of symmetry that we could use these coordinates to represent. And so I could write this in terms of, instead of x and y, I could write it as minus advective velocity in the longitudinal direction, dc dx, so it is x, minus advective velocity in the transverse direction. It's not an exponent, it's just a concentration in y, plus, we called it d star, I think, right, in the previous one? Where is it? This. Plus d star d2c dx squared. Again, we don't care much about it. But we do care maybe what it's called. So it's called the advection diffusion equation. Don't have space. And it represents those two processes. And so the idea is that we can use this expression now to put boundary conditions on it and solve it if we wanted to. We won't, but we'll use other people's solutions. It always looks like this. This represents the dissolved mass that's carried in by the water flowing in one side of the beaker and flowing out of the other side of the beaker, if we look at it ensemble. This is the amount that diffuses in by Fickian diffusion, and this is the difference between how much goes in by both of these mechanisms and comes out is the accumulation, this term here. And so that's all we need to really understand about that. So now what we can do is see what each of these portions mean. The advection term is what gives you this sharp front. If, for instance, this term d star is 0, then you'd get absolutely a sharp front for one-dimensional flow. So I know I said that we should think about it in plan view, but let's think about it in the same flow domain that we had before. So this would be x and longitudinal, y would be transverse. Actually, nothing can happen in the y direction because we only care about it along the core, and we'll assume that every other section in the y direction looks the same. And so you could imagine that if you set d star to 0, you'll get a front that looks like this. If you imagine the velocities being 0, then this is the case where the velocity was 0. It starts off with this, and it slowly spreads further and further. You could imagine this slowly spreading out like this with extra time, right? T1, T2, T3, T0 roughly, if you collapse that down. So this has no bulk motion of water carrying the fluid and looks like this. And so that's exactly what this curve here is. So if you started it off at, without any velocity in it, if these were both 0, then you'd get the green curves that you have here. And so if you put these two together for a real system where you have both advective flow downstream at some velocity and also diffusion occurring, you get both cases superimposed on each other. So this front would be for d star equals 0. And this would be for increasing d star. It's not done in a vacuum because it's probably relative to the magnitudes of these velocities. It probably matters, the ratio of these two might make a difference. And I suppose, although I haven't drawn it here, you could imagine that this is exactly what has the effect on the arrival time distribution, which instead of being this, might be, in different cases, this. This would be 1, this would be a half, this would be 0. And so here's some curious things, right? The water's going downstream, but for some reason, it's got ahead of itself in terms of diffusion. Well, that can occur, of course, because we know that even if water isn't flowing, it can move downstream on its own by random walk, Brownian motion. So this is a function of the fact that the concentration gradient, and of course the concentration gradient here is infinite. This is dc and this is dx. So dc dx goes to infinity, right? At this point here. And so that means the diffusion driving the mass transfer ahead of the front is big, but can't reach very far. But the mechanism is exactly that. So this is the result if we solve this equation for the boundary conditions of some concentration here and an advective velocity in the x direction, or what we will call the longitudinal direction. So this is exactly what we have. If you think about the input function being slightly different, so in other words, you put something into the ground, it dissolves into the water, and you put so little into the ground that it's all dissolved into the water and there's no source left upstream, as there was here, then you can imagine that this would be a source that's turned on and then turned off straight away. And so what you'd expect to happen is it's carried down gradient by the velocity, so it will migrate downstream as this skyscraper. But because there's only so much dissolved mass in this, under this curve, the skyscraper, then just like the ink bubble, as it only has a set amount of mass, as it spreads out wider, the peak has to get shallower, because the area under this curve, you could imagine, as being equivalent to the area under the red curve, right? Each of these curves should kind of have the same area around them, because a differential unit of length, this is a bit dweeby, I guess. So this quantum of concentration in volume has to be present within this red curve, and as it spreads out, it might get to be lower concentration, but it's filling more volume. And so you can imagine this being the number of bricks that make this up at a certain concentration gets spread out. That's actually not a very good analog, I realize now, say that, but anyway. And again, and so we'd like to be able to use this location as how far it's got downrange as the product of the advective velocity and times time. It's the same as you've done here for your arrival curves, right, for Yucca Mountain. That's nothing other than this. This time is equal to what? Velocity is equal to length over time. So time would be equal to length over velocity. Not smart enough to remember that, but know how to get it. And so these are the behaviors that we'd expect. So what we'll do is we'll try to get these behaviors for real systems and see what the controls are. In the meantime, we've made the point that at vector velocities we know, effective diffusion coefficients we kind of know because we've said something about Fick's law. But we've also said that there's an effect that we need to account for, and that is mechanical dispersion. And so we'll find that Fick's law really only acts as Brownian motion if it's not going anywhere, if the water is stagnant. If the water is not stagnant, then we'll get something that looks like Fick's law, this so-called mechanical dispersion, but is really a different mechanism that just happens to look like the fact that we have a blue skyscraper turning into a red mound because of this as we go from location to location downstream, whereas before we had it within a beaker that wasn't moving. And so what we want to do is be able to characterize this effect of mechanical dispersion. So we should understand what drives it. Pretty straightforward. You could imagine that these three mechanisms might contribute to it. One is if you have superhighways with open pores and it can go very quickly downstream versus very slowly downstream, then this dissolved component would arrive downstream much earlier than this one, and therefore there'd be a separation between those, so it's spread out. If it's going on a path which is different between different molecules that start off here, you'd also think it's spread out, like our little diagram showed. And also, you could imagine that within pores, this so-called Taylor dispersion, the idea is that if you look across a pore, there's a velocity gradient. You know from flow in a pipe that the velocity across a pipe is 0 at the boundaries of the pipe, if we solve Navier-Stokes, and maximum in the middle and kind of parabolic. So you can imagine if something's being carried down at this 0 velocity, it doesn't get very far close to the wall. But if it's in the middle of the river or the tube, then it goes really very quickly. And so the concentration would spread out downstream. So this is low concentration and maximum concentration in the middle. However, all of these things together are kind of complex, and we don't know what the porous medium looks like. So we just take the idea that as we go downstream from one point and we get spreading occurring, if we can measure the amount of spreading we get in a real porous medium and fit it to this model of d2c dt dx squared, sorry. If we can fit it to this model of what we think it's going to look like, such as this arrival curve, then we can choose to use an equivalent magnitude of this term here. I won't put a subscript to it. We could calculate what this equivalent magnitude is that accounts for this mechanical dispersion. And if we look at the upstream section and the downstream section, this would be the change. If we looked at the profile along its flow path, then this would be the change. This looks exactly like this behavior, and we've said that this equivalent diffusion coefficient or dispersion coefficient is a measure of this flattening out of the curve. So that's really all we're trying to determine. And the approach we use is just to use a representation to realize that, as you think, if the water's going through this packed porous medium faster, the spread might be larger in some proportion. We don't know what that would be, but it would make sense that that's the case. Okay. And one way to do that is to look at this proportionality. So we use a dispersion coefficient, longitudinal dispersion by alpha L, transverse dispersion by alpha T, and we put them as a coefficient, which we don't know yet, and being proportional to the velocity at which it travels. And so if we redraw that picture I had before, we have x and longitudinal, we have y and transverse, and we expect the plume to kind of look like this. I guess if we drew a section through it, the middle, it'd look like this. Whoops. And if we drew a section across it at different locations, it would look variously like this. I've run out of space, but I'll do it here anyway. And like this. And it's merely conforming to the idea that we have this behavior d2c dx squared equals dc dt, and some longitudinal dispersion coefficient, which governs this spreading out of the plume and how this behavior occurs on this front. And so if we take it on trust that we can relate this mechanical dispersion to a longitudinal dispersion coefficient and a transverse dispersion coefficient, where it's a function of a material property of the aquifer and the velocity at which, this is the advective velocity, in the x direction, or the longitudinal direction, right? If this is flowing in this direction, this is a velocity. Orthogonal to that maximum velocity has to be zero velocity. So the velocity in y is zero, so we can't use that. So this has to be the velocity, the maximum velocity in x for both of them. I guess that's important to realize. And these are coefficients which we need to get somehow. Turns out that maybe transverse is a third of the magnitude of the longitudinal one. We'll see what that is later. And if we use that, and if we use these coefficients in this expression here, in this expression here, then we can accommodate that behavior. So let's write that out. So let's assume that we can fit those data. So now we know that we can have mechanical mixing occurring, and we can also have, at the same time, diffusion. So if the water's not moving at all, then we'd expect there to be no mechanical mixing, but we would still get Fickian diffusion by this equivalent magnitude. So I guess if in clays the velocity of advective velocity was zero, we'd lose this term, and then the longitudinal dispersion would just be equal to d star. This is molecular diffusion in a tortuous pore space, which we said was equal to the real diffusion coefficient multiplied by some factor. So if that's the case, which is a small number, so this we said was something like 10 to the minus 9 meters squared a second. Take it on trust, it's a small number. If we now have a high velocity in sands or gravels so that the velocity is high, then all of a sudden this term becomes finite, and it may be, we don't know, it turns out it does, it becomes much bigger than this. Even for small velocity, this term will end up completely overpowering this. So this represents the two regimes. When no velocity, it will be diffusion dominated, and when you have velocity, this term becomes inconsequential, and this coefficient describes the behavior. And so, so it allows us to be able to watch behavior as we go downstream. So what you could do is you could do an experiment where you define this value. So you just said that the total dispersion coefficient is equal to the mechanical part plus diffusion. So what you could do is you could run an experiment by flowing fluids along here at different velocities, and at the output, I guess you can't really do it inside the sample. Inside the sample you could measure the concentration, not very easy to do. Or more likely at output you could measure how the concentration changes with time. So this is concentration, this is time, this is location. And so this is the breakthrough curve, or it could be this. So intrinsically, whether you get the red or the green says something about the value of DL, right? If it's green, then DL is large. If it's red, DL is 0. And so what you could do is measure the diffusion as it comes out for a whole bunch of different velocities, and then plot this, the dispersion coefficient relative to what we've called D star. On this diagram, it's called DL over D lowercase d. Right? Same things. So when the velocity is 0, this is the velocity, this is the diffusion coefficient, advection velocity, and this is the pore diameter, so it's some normalizing factor. You'd expect that when the flow velocity longitudinally equals 0, then dl equals dd, and dl over dd equals 1, right? So when the velocity is 0, it won't be that it travels at 0 velocity, because it will diffuse by Fick's law. So you'll see coming out of it the fact that it's diffusing at some rate, which will be the diffusion rate dd, and so this ratio will be equal to 1. As you increase the velocity, then all of a sudden at some magnitude, then as the velocity gets to be a big number, then the measured diffusion dispersion rate will be equal to alpha L times V plus this. And of course, that last parameter goes to 0. And so if you divide this through by dd, I guess this becomes 1, and this is the trajectory. So it's 1, this becomes 1 plus here. So this is the value for diffusion only. But as you increase this velocity, at some stage, this mechanical dispersion term becomes large enough that it completely swamps this, and you go off on another trajectory. And that other trajectory is this. There's some kind of transition. So this is the regime which is mechanical mixing dominated. This is the mixing which is Fickian diffusion dominated. And with a single expression, you're able to represent both of those behaviors for the changing velocities in the system. You'd expect that if you look at, not in this geometry, but if you looked at the geometry of, if this is a very wide cylinder, and you looked at dispersion in the transverse direction, then you could also use this, do this measurement. And it would look the same, because we're doing the same characterization. The fact that when you get diffusion only, it's independent of velocity, because velocity is not big enough to make it mix mechanically in the pore space. And as you get above a certain threshold velocity, which looks like this threshold is about this magnitude equal 1, actually this magnitude equal 1 here as well, right? Kind of, in both of these cases. They're on different scales. So this is about 1. This is about 1. And then you get this same behavior. This would be 1. This would be diffusion. This would be advection. It may be that it's 10 that it crosses over, it doesn't matter. And actually this number is a significant number for us. We'll call it the Peclet number. I think it's an acute on the last graph, which is the ratio of advective flux, the amount of mass carried by advection, divided by the diffusive flux. When the velocity is 0, Peclet number is 0. It's off on this side somewhere. When the advective flux dominates, it means it's a large velocity, and it's over here. And that's given by this number. It's given by an advective velocity. It's given by characteristic dimension, which happens to be the grain size here. It's not always that. And it's a diffusion coefficient, which we've called d star, but they call d sub d. So this is the effect of diffusion. This is the effect of advection. And when these ratios are a bit like a Reynolds number, right? A ratio of inertia to viscous forces. They're in the same units, so that by definition they're dimensionless, and it controls this switching between behaviors. And we'll use that to be able to tell ourselves when the behavior looks like this step function, which it does sometimes, and when it really doesn't look like that step function, where it canters over and arrives early because of diffusion ahead of the front. And in some cases, I guess we'll see also that the curve actually looks like this. So this is useful because at least at this time when you're expecting to arrive, you come up with the average concentration arriving. So the kind of average concentration at the front is arriving at the time you predict it. But in some cases, it's going to turn out that your prediction of the time at which the average concentration will arrive will be much later than this. So the curve will look, it won't intercept at this point here, but it would be something on here. Don't need to do that today, but that's what we'll do later. So next time what we'll do is we'll take this expression at the top, and we'll try, we won't solve it ourselves analytically, but we'll look at what the solutions like this look like. It turns out that they look like this figure here, which is the residence time distribution. This is 50% concentration. This is 1 pore volume. And so it shows that for some Peclet numbers it works just fine. For lower Peclet numbers, it doesn't work fine at all. And so we'll kind of pull out exactly what that means next time. Okay, great. Questions? I should look up more to see what you're up to. Anyway.